much today. Like for you guys, pay attention now. Follow along with me. And again, if you're not paying attention, if you're not going to look at these notes Friday, you're going to lose points that are really simple, really easy. So just follow along with me. There's no assignment. This is just a lesson for today. Again, if you cannot get that file to open or to work, you might want to take notes on paper on things that you can't get to operate. Kids at home, what do you see? I need a. I got too many things opening here. All right, you guys should see my PowerPoint right there. I'm going to present it. And hopefully kids at home, hopefully see the whole PowerPoint. So there are going to be interactions with this. And I would like for you guys to help me with the interaction. I know all the answers, but I'd like for you guys to tell me what goes in the blanks and what does stuff. There's going to be a lot of learning checks here. There are going to be some things that you might want to remember, hint, wink, wink, especially for Friday. So rates and reactions. What we're going to be talking about this week, we're going to do a lab on it Wednesday, is exactly what it sounds like. The rates of a reaction. How fast, how slow, how reactions are working. Okay? There are lots of things that go into a reaction in chemistry. But a reaction is essentially, in order for it to happen, you have particles that are going to react and mix together, and they have to hit, they have to touch, they have to collide. If I have particle A in my hand and particle B in this other hand, and they never touch each other, they're never going to react with each other. Okay? Just like your hand on a hot stove, okay? Your hand and a hot stove is never going to react together if you don't touch it. Thankfully, that's a good thing. Okay? Same thing in chemistry. You have particles that need a hit, that need a touch in order to do things. Okay? And I have a whole closet of chemicals not touching each other. Again, that's a good thing. If I let them touch each other, that closet is going to be going crazy. Okay? And again, that's what a chemical reaction essentially is. So the speed of a chemical reaction varies widely. You can make chemical reactions go very slow, take years upon years. You can make chemical reactions happen very quickly, even what you might think of instantaneously, immediately. Okay? Some are very fast, some are very slow. And that speed is called the rate of reaction. And so essentially, some examples, rate of reaction, rusting. However, you might say this is not necessarily a slow thing. If you ever leave your dad's hammer outside, it'll rust in one day. If you don't believe me, do it. Take a hammer, put it outside tonight. Tomorrow morning, it'll have rust on it. Okay, so rusting is actually kind of a slower process. It does take some time. But rusting essentially is the oxygen in the air and the moisture and water is reacting with metal, especially raw metal, like a hammer or a nail. The rusting is kind of a slower process. Baking is a chemical reaction. When you bake, when you cook, a lot of cooking is chemical reaction. And so a lot of chemists are really good at cooking because that's what it is. Okay? They follow recipes, they follow rules. That's something that happens quickly, fast. Explosion, light, energy, heat, fireworks, something like that, they happen very, very fast. Again, what you might even think of it as an instantaneous reaction. Something that happens that instant, right away. That's a super fast reaction. So the question is, why are some reactions faster than others? And that's what we want to dive into, is the rate of reaction. So you have these particles here, you have this little picture. They're playing bumper cars. It's going to kind of be our example or model for today. Okay. Can you take a wild guess what the red and the blue particles are representing in the picture? Yeah, they're temperature. Hot and cold. That is one example of a reaction rate. If we have things that are hot and cold. So we got these little guys holding a hot cup of coffee, it looks like. We got these guys holding an ice cream cone. So we got hot and cold molecules. Okay? Is that going to change our reaction rate? Well, maybe. Okay. So reaction, again, is the amount of time it takes for particles to collide and react together. If you don't let them collide, the reaction rate will be forever. Okay? It will never happen. So it's the amount of time it takes for particles to collide and react together. Okay? And that also is going to require energy. Okay? And again, you might be the energy. You might be the one mixing them together. That's energy. You are putting the particles together. Okay? Well, maybe you do other things to add energy to it. But all reactions need a certain amount of energy to get started. And that is called activation energy. That's an important word. That's the word you're going to hear a lot today and this week. Every reaction has an activation energy, the amount of energy it needs to start. Some reactions need very, very little energy, especially things that are combustible. Things that are combustible, all they take is a spark and boom, they go. A little bit amount of energy and they can go up. Okay? Some reactions need a ton of energy. They're extremely difficult to do. Okay? And again, oftentimes we humans have to add that energy in order to make it happen. And sometimes reactions require so much energy that it's not worth doing at all. Like we could do nuclear fusion, we could do nuclear reactions if we want. They require such a large amount of energy, it's not really worth it most of the time. Okay? So there are two main things that reactions require. One is the frequency, how often they're hitting each other, and the amount of energy you put in to make them hit each other. And that is all that's required in a chemical reaction. Can you make them hit each other often? And if it's not enough, add energy to make them hit each other. And again, it could literally be you stirring it together to make them hit each other. That is energy that you're adding. Okay? If the particles collide with less energy than the activation energy, they won't react. Okay, they just barely bump into each other, like, nope, that's not enough energy, not enough energy. They won't do anything. Okay? They'll basically just bounce off of each other. All right, so anything that increases the number of interaction collisions is going to make the reaction more likely to happen or make it go faster. So those things are going to be things like increasing the temperature. We're going to look at that in a second. You can also increase the concentration, the amount of ingredients you put in there. You can also increase the surface contact, okay, surface area. And you can also use a catalyst. A catalyst is something that makes the reaction go quicker. And we'll look at those in a little bit as well. All right, reactions do not, we're going to look at a graph here as well. Reactions do not proceed in a straight line. And they will oftentimes start faster and then end slower. Okay, they take a certain amount of energy, and as they use that energy, they start to relax or slow down. Okay? As the reaction occurs, you're going to have less energy, you're going to have less reaction. And this picture should make sense to you. At the beginning of the reaction, we're going to have our reactant 100%. We have no problems. As they start to react, they're going to lose energy, and then they're going to lose the reactant, and eventually to become all product, the new substance that we have. So a reaction, because I have a bunch of reactants, tend to go faster, and as I get less and less and less, it's going to chill and chill and chill. And eventually the reaction will totally stop, because I have nothing left to react. I made all my product. Yeah. And so we end up with a graph that looks like this. Here, almost always, when we're looking at the amount of product versus time, the reactions start faster and then get slower and slower and slower, and eventually the reaction stops. This reaction should be very quick. I mean, like almost instantaneous. Reaction should be very, very, very long. Okay? So this graph can change depending on the speed of your reaction. And again, we have to calculate that as well. We calculate the rate. You guys in math class probably know how to calculate the rate. Okay. Again, this picture here is also showing you the particle that you have. At the beginning, you have all reactant, and then eventually, as you get less reactant, the graph just starts to chill, and you come to an end where it's completely and 100% the product. All right. So when you measure the reaction rate, and we're going to do some of this, and it's not typical. When you measure the reaction rate, you need to be able to measure time, but you also need to be able to measure the amount of reactants versus products that you have. So if we have this reaction here, magnesium and hydrochloric acid, that's going to react to make magnesium chloride and hydrogen gas. I can measure the amount of hydrochloric acid I'm using and how much I end with. And I can calculate a rate. I can measure the amount of product I'm making, magnesium chloride, and I can calculate the rate. I can measure the amount of hydrogen I make, and again, calculate the rate. Okay. These are things we're going to do on Wednesday when we do our lab. Okay. So for example here, I have hydrochloric acid, I have magnesium. I could actually collect the gases in here. I could have a stopwatch, and I could watch the plunger get bigger and bigger and bigger as I make more and more hydrogen gas. And I can get a stopwatch and say, okay, how long does it take to go from 0 to 2? How long does it take to get from 0 to 4? How long does it take to get from 0 to 6? Okay, making more and more and more hydrogen. Eventually, this plunger is going to stop because the reaction is done. And then I'll know that the reaction is finished. And the reaction took 20 seconds. And I can figure out the rate of reaction, again, by graphing it. Time versus product. And then the rate is your slope, rise over your run. So how long did it take? Okay, how much product did I make? Divide out the product by this time, and you can get a reaction rate. This number is going to be higher than this number because this is going to be 0. Okay, there's no change in my reaction rate at that time. Flat. So you can always do a rise over run, a slope formula, to figure out your rate of reaction. I know I'm going kind of quick here. We're going to summarize this up here in a second. And we're also going to go from there. So let's clear this real quick. All right, so here is a picture. Let's fill in the boxes. So you got to do this with me. Kids at home, put it in the chat box. All right, so this box you have right here, where do you think it falls on this graph of the amount of product versus time? So I got 2 blue, 2 reds, and 2 purple. Which one? That one? That one? No? All right. So this will be a second one over there, but yeah. All right, we'll try that one there. All right. What about this one? Where do you think that one goes? So this is all products, or all reactants. All red, all blue. That's going to be the very first one. The arrow is kind of weird on that one there. All right, this is all products. Okay. Well, this one. Mostly reactant, but it's got a little bit of product in there. And this one here. All right, I think we got that one right. Let's check it with the C on there. All right, so we got that on there. All right. So again, this is showing the amount of product that we have versus the reaction rate. And again, when we get up with all product, it's going to be done. It's going to be finished. All right. So here is a little summary on reaction here. So there's a little word bank. And again, you could do this with me if you follow along, if you get it to work. Again, if you see a black box here, you got to give it permission to run, download the Flash. The chemical reaction only takes place when reactant particles do what with each other? See that? See if we can drag that up there, collide. We'll check on that in a second. All right, particle must collide with enough temperature, frequency, Energy. We got to think. All right, let's try that. This is called the blank energy. All right, that's the activation to get it started, the energy. Oh. Stop it. My fingers. Okay. So the rate of reaction depends on what? The what? We got to think. There are two things that reactions depend on. So it's how often they hit to frequency, and then the amount of energy they hit with. So frequency on that. So changing the blank affect both the frequency and the energy of collision. What do you guys think? So what is going to change the number of times they hit and the amount of energy? All right, let's try that. Let's try that. Just because it's there doesn't mean it's right, by the way. We'll check it in a second. Changing the blank affects the frequency of collision and dissolved reactants. So we have, to the left, we have concentration, surface area, or bond. Is there surface area in that one? It's not letting me do that one. Surface area is going to be in a solid. So there's going to be concentration. So if we make more, we put more of it in there, it's going to change the reaction frequency. And then changing the surface area is going to allow the frequency to of a solid to increase. So if I have a piece of aluminum, I can flatten it and make it really, really wide, and it will react a lot faster, a lot quicker on that. So again, this is a learning check, one that you might want to take a look at for later. All right, temperature. So this picture kind of represents temperature. You guys know temperature, even with your own bodies and stuff, this happens to you. When you get cold, your body tends to tense up. It tends to harden, it tends to tighten up. That's a natural reaction to your body. Things tend to slow down when things get cold. When things get warmer, tend to be more active, spread out, tend to move a little bit more when things get warmer. Okay? And the same is true for this picture here. Okay, so things that are cold tend to stay put. Things that are hot tend to move a lot faster, a lot more. Okay? So the higher temperature rate, the higher the rate of reaction. The more temperature you put in there. So literally, heat it up with the max, heat it up with the flame. Okay? And many reactions, for example, if you increase temperature by 10 degrees, you'll double the rate of reaction. And there is a formula for why that happens there. And again, basically, when you increase temperature, you're increasing energy. Okay? When things get hotter, they have more energy, they can do more stuff. Okay? When they do more stuff, they can collide more often, and that will increase the number of reactions that we get. So here we have the same number of particles. Same number. We got low temperature, we got high temperature. We're going to let them go for 15 seconds. What do you think is going to happen with the number of collisions? Who's going to have a higher number? The cold stuff or the hot stuff? Yeah, watch them. They're going to go, these guys are flying around. The low particles are going nice and slow. You know, they're cold. They're not going to collide. They're not going to hit as much. Okay? And again, this is collecting data on the number of collisions, high temperature versus low temperature. The more they can collide, the more they can react. And by the way, this is random, kind of. So if I did it again, it would not get these same numbers. It's literally testing the randomness of these particles as they move higher temperature or lower temperature. Okay. So here's a question. Why are batteries more likely to run down more quickly in cold weather? You guys probably have experienced that, car batteries especially. Car batteries like to die quicker in cold weather. They do. So why is that the case? It takes more energy to stay hot. Okay? So we're talking about electrical energy. We're talking about the movement of electrons. Electrons have to move to make electricity. So when it's cold, what's happening to the movement of the electron? It's slower. They don't work as well. Right? You can get it cold enough where the electron won't flow at all. Right? Now, normally, as your car warms up, the battery warms up and it's perfectly fine. Okay? But batteries in cold weather have a hard time because the electrons just don't want to flow. They don't want to work. Okay? Now, if you want to make your battery last longer, so for example, let's say you bought a pack of AA batteries, but you're not going to use them yet. You can put them in the refrigerator. Right? Put them in the refrigerator. They will last longer in the refrigerator. However, when you take them out of the refrigerator and you pop them into your game controller or whatever, they might not work right away because the electrons don't want to flow right away. Okay? But they should still be good to go, though, once they warm up. Okay? So batteries do work a little bit better in normal temperature than they do at that. Okay? So again, the reaction within the battery is just slower at cold weather. Okay? And the electrons just don't move as much. It does not make as much electricity. Okay? So they might not have enough energy to start your car. So all you gotta do there is warm your car up, let it run for a couple minutes, and it should be fine. Again, assuming you can let it run. All right. So for example, in this reaction here, okay, we have sodium thiosulfate, hydrochloric acid. Gonna make a couple of different products, quite a few different products here. So we can actually change this to make the reaction go a little bit quicker with some heat. Let me go back here. I think I lost one there. All right. Okay. So this is actually showing you a little bit about what you could do for how to determine how temperature affects the heat. You can actually do this by drawing on a piece of paper. Okay. We're not going to do this lab, but anyway, all right. So we have a Petri dish here. So over time, the dish starts to get cloudy in there. You can actually use a stopwatch to measure how long it takes to get cloudy. And then we can actually warm up this. We can actually put it on a hot plate and do it again and again and again and again and again at different temperatures. And we end up with a graph that looks something like this. Okay. So as we increase the temperature of that cloudy solution, it gets cloudier and cloudier and cloudier, faster and faster and faster. Okay. It's a really common little demo on that. Again, if we look at the table again, we can see that there is kind of a pattern, a trend to the graph. Eventually, it will kind of start to it will flatten out, as you can see. Not necessarily exponential, but it's kind of in that way, kind of parabolic, so to speak. It will eventually flatten out. And you can probably imagine that regardless of what temperature you have, it's probably going to take at least 10 seconds, no matter how hot it is. Right? It'll probably flatten out around 10 or something. Okay? You never get to where it'll be instantaneous. It happens in half of a second. Okay. All right, we also have concentration. Concentration means you have more particles. That should make sense. If we have more particles, we're going to have more collision. Right? So lower concentration, higher concentration, more particles involved in the collision. So again, if we have lower concentration, we only have we have 8 particles here. I don't know how many we got there, about 20 or something, but we have more particles. This time they're the same temperature. So if we run this, they're the same temperature, they're moving the same rate. Okay, that red bulb is moving the same speed as the others. But you see, when we increase the concentration, we get a lot more collision when we increase the concentration. So there's just more particles. There's more stuff within that area. Okay. All right, so we have this lab here. Magnesium ribbon versus hydrochloric acid. What happens if we increase the concentration of, especially the hydrochloric acid? Here, so we got these little flasks. We can actually pick it up. We can actually drop it in. Okay. And we have to literally time it. How long does it take to make this hydrochloric acid, this gas? See the gas formation happening? You see the plunger getting bigger and bigger and bigger? Okay? We run it for 1 minute. It makes 14 millimeters or 14 cubic centimeters of hydrochloric acid. So, total volume of hydrogen. We can continue to do that if we increase the rate of, if we increase the amount of acid we have. So this has 1 molar acid, it's 2 molar. We double the concentration. We know that the reaction gets faster if we double the acid. And we can do that. And again, that should make sense there. We double the acid, double the reaction. Right. All right, we don't need to see that again. All right. We can also do the same thing with pressure. Pressure is where you take the volume of something, you make it smaller. Whatever it is, okay? You put pressure on something, you make the volume smaller. So in this situation, we still have 6 particles. 6 particles, 6 particles. Low pressure, volume bigger. High pressure, the volume is smaller. Putting pressure on the volume. Okay? So same number of particles, but in a high pressure situation, they're going to react more because they're closer together. More collision to happen. All right, surface area. So we have this picture here. If I drop one, they're all the same size. They're all the same amount. But if I drop 1 block versus 4 blocks, and if I drop it into acid or whatever, which one's going to react more? The 1 block or the 4? Yeah, the 4. The one with more pieces, right? They're going to react more, they're going to react faster. I can either take that block, I can make it into 8 pieces, 16 pieces, 32 pieces. I can make it into a powder with no pieces at all, just a bunch of powder. And it's going to react faster and faster and faster with that. Okay, so increasing the surface area allows for more particles to interact, to collide. And again, more particles hit, the more the reaction takes place. All right, so in this one here, I have the same number of reactants. 6, 9, 9. I got 9 reactants, 9 blue, 9 red. How often are they going to hit these boxes? Again, we can run this. Right? They're all going the same speed, the same temperature, but there are more boxes, more surface area, there's more collision with that green stuff, whatever that green stuff is. Okay? And you can imagine if I did 8 boxes, they'll hit all the time. If I did 20 boxes, the boxes would be everywhere. They'd be hitting non-stop, right? If I put that green stuff everywhere as a powder, they have 1 million collisions, right? So the smaller you make it, the bigger the surface area, the more reactions you're going to end up having, the faster it will be. Okay? So this one here is marble with hydrochloric acid, also known as calcium carbonate, like chalk. Okay. So if I take a piece, sorry, I got started. If I take a piece of the chalk, by the way, I'm just going to do it by itself. Okay. So I have this little piece of chalk, it's bubbling, reacting with the acid. Again, I can time it. How long does it take to dissolve away? I can actually see what's happening to the mass. Now, why is the mass decreasing at this spot? Why is the mass going down? Yeah, I'm creating a gas. The gas is leaving. Gas is going away. So the mass is decreasing, decreasing, decreasing. And so that was the big ships. If I do it with the small ships, the gas happens a lot faster. Okay? But note that they all end at the same place. So they have the same amount of product. They all end at the same place. But the small ship goes faster than the big ships. And that actually might be allowed to do on Wednesday, depending on what happens. The last one is called a catalyst. Catalysts are substances that we can add to the reaction to make them go faster. And often they're chemicals, often they're acids. I can make them go quicker. What they do is they lower the activation energy. How much energy do I need to put into it to make the reaction go? So note that we start and we end with the same thing, but the amount of energy I have to put in can be different. That activation energy. If I lower the energy, make the reaction go easier, make it go quicker. We're going to look at a lot of these graphs. This is the activation energy, EA, activation energy without a catalyst, activation energy with the catalyst. Note that this reaction is much easier, much quicker, much faster than that reaction. Okay, so a catalyst is typically a chemical. Doesn't change the reaction, but it can do stuff. Metals are oftentimes catalysts. Nickel is a common catalyst. When you're making butter and margarine and things like that, you add nickel to it, make it happen a lot quicker, a lot faster. Iron is a catalyst when you're making ammonia. Platinum is a catalyst, especially for cars. Catalytic converter. It's taking the emission from your car and changing it to carbon dioxide and water a lot quicker, a lot faster. There's actually quite a bit of platinum in your catalytic converter. Don't just throw that stuff away when you're done with it. All right, how much time we got here? 1 minute. All right. So catalysts are important because they make reactions go faster. It's going to save you money. Oftentimes, it's going to make things faster, quicker, save you money. And it's also going to, allow your reaction just to go easier. So they're very, very common for that. Okay. All right, we'll talk a little more about this tomorrow with some summary stuff. But you guys have these notes. I know that took a little bit of little bit there. I like those demonstrations though. If you can get those to run and play with them, kind of really help you understand the rates of reaction. Lab on Wednesday. I don't know what, but lab on Wednesday, depending on weather. All right, you guys are good. Get out of here, and I will see you guys later.